Yeah, okay. So the idea was if you have IID variables, this example we did, for example, they're Bernoulli, you take the average. Uh, the weak law of large numbers tells you that this converges in probability to the expectation, the common expectation of them, which is in this case would be the probability of A. But this more general principle can be used to compute integrals because expectations are integrals. So imagine you have an integral like this. You want to compute the integral of a function gu from 0 to 1. Um, a priori, this doesn't seem to have anything to do with probability, and it doesn't necessarily. But then you can write it as the expectation of g of u, where u is a uniform random variable. So if you remember the uh, density function of this random variable would be just 1 if u is in 0, 1, and 0 elsewhere. So when you try to compute the expectation of this GU, you're basically doing integral of, this is the law of unconscious statistician, right? du, and this is just 1 over 0, 1, and so you just get this integral. Okay, so you can write an integral as the expectation of a function of some random variable, in this case it would be uniform. And then the law of large numbers tells you if you have IID samples of this is a new random variable. Let's say this is x. If you have IID random variable, sorry, IID draws of x, then you can use the law of large numbers to approximate this integral. So a way of doing it is just to draw u1 up to un independently uh, from the same distribution, right? So independently and all uniform. And then estimate the integral like the sum. Sorry, the average of them. Okay, so by the law of large numbers, this would converge to the expectation. So it's like converging to the expectation of any one of them, let's say g of u1 or u2 or whatever, and then this is exactly the same integral. Okay, that would be this integral. Um, and then you can also talk about the variance, how variable it is. You can use Chebyshev together the variance to quantify the difference basically in probability, like how likely you're away from the actual integral. And the variance would be the variance of this divided by n. That's kind of from the idea that we know already. So variance of the average is the variance of one of them divided by n if they're IID. Okay, so basically random sampling turns integration into kind of averaging, basically. And this construction works in RD as well. If you think about it, um, doesn't have to be integral on 0, 1. It could be integral on the cube, unit cube in RD. You take a um, d-dimensional uniform random variable on the cube. Um, and the interesting thing is that the rate would still be this rate. Okay, so that's the rate of the standard deviation. So how fast the variance goes down is going to be still like 1 over n, or the standard deviation would be this much. And this doesn't depend on dimension, which is pretty interesting. So it's like dimension independent approximation. This might depend on dimension. The scaling in n doesn't. Um, so here's an example. So to estimate the pi, um, you can draw, let's say ui and vi, a pair uniformly in the unit square. Okay, they're independent and right, okay, there are different ways. So you can say, okay, the pair is uniformly distributed on the square, or you can say individually each piece is uniform on 0, 1, and the pairs are in like basically the coordinates are independent. That's the same effect. Either way, so you can say jointly uniform on 0, 1, or marginally uniform. So uniform on the unit square. or marginally uniform on 0, 1, but also independent of each other, has the same effect. So you do this, if you look at it, you get, if you sample, you get these points, and then you can define an indicator that basically is activated when ui squared plus vi squared is less than 1. This is telling you that this point lies inside the unit circle. Okay, so the points here that are um, green are the ones that satisfy this. So for them, this indicator would be 1. For the other ones would be 0. Okay, and the expectation of this random value, they all have the same expectation. Doesn't depend on I, so it would be the probability that this is less than or equal to 1. And if you, again, remember what this is. This is going to be integral the joint density of ui and uvi. Let's call this uv. And then times the indicator. Um, or you can say we're integrating it over this region. So the region in the, let's say this region in the plane where u squared plus v squared is less than or equal to 1. This is the inside of the circle. Um, and then u and v are bigger than or equal to 0. Let's call this c. So you're integrating this over c. And it's going to be du dv. And this is going to be, because it's uniform, it's going to be 1. Because the unit of square has mass 1, like area 1. The density would be 1, so you're basically integrating, it would be just the area of C. Okay, so this probability is really going to be the area of basically that C is this half, or like quarter circle. And we know that that's the pi over, is it pi over 4? Is it correct? So yeah, the area of a circle would be pi r squared, and r is 1. So the area, the whole circle is like pi, and so pi over 4 is the area of this part. So what happens is that, if you look at the averages of these, so this is the average, the empirical average of the indicators, that would be um, converging to pi over 4. So if I multiply by 4, that would give me an estimate of pi. Okay, so this is going to converge in probability to 4 times the expectation of one of them, which is pi over 4. So it converges to pi. So this gives me an estimator of pi as like average of these indicators. And here you're plotting that. I guess you can see it's like it's stochastic. So if you plot it as a function of n, as you get more and more points, it becomes more accurate. So initially it has like fluctuations. And if you do it another time, you get another path. It starts to narrow down, because the probability is basically like the probability that you're within epsilon of pi will be shrinking. That's what we have seen, right? So that the probability that pi hat n minus pi is bigger than epsilon is going to go to 0. That's the meaning of conversion probability as pi goes, as n goes to infinity. So if you look at an interval um, of length 2 epsilon centered at pi, um, the majority of these would pass through this. Occasionally you might go out a little bit, but uh, you can compute exactly the probability. Like that would give you the fraction of the paths that stay within or like violate this. Like Chebyshev, for example, gives you, I mean, in this case, they're more than Chebyshev, because this is like an indicator you have these exponential bounds even. We briefly talked about that for the binomial. You get a better bound generally. Um, Questions about this? So that's the general idea of Monte Carlo. So you can use the law of large numbers to approximate integrals by randomly sampling IID variables and then taking averages. So if you use the Chebyshev, you can provide some sort of like an approximation. So I'll let you figure this out as an exercise. So how large n must be for Chebyshev to guarantee that the error is below like 0.05, for example, with probability at least 95%. Okay, so this would be 0.05. And this would be less than or equal to zero point zero 0.05 as well. It's like 1 minus 95. So you can figure out n if you kind of compute. I mean, you can like upper bound the variance basically. The variance of a Bernoulli is upper bounded by 1 over 4. So using these, you can kind of compute. I'll let you do it. Like, just maybe verify that n has to be bigger than this. Okay. Any questions about this? Is just an application of the law of large numbers that was remaining from last time. Okay. Questions about this? Law of large numbers. So the rough idea of the law of large number was that independent centered like noise accumulate at the scale root n. So if you remember the Sn, the sum of the IID, zero mean random variables, let's say if you look at this is scales like root n because the standard deviation is root n. And the average with a scale like sigma over root n around the mean. So if you look at the average minus the mean, this behaves like sigma over root n, the error, because the standard deviation is, or the variance is sigma squared over n, and so the standard deviation is sigma over root n, so it goes down. And so this suggests that, okay, let me maybe briefly mention also that dependence and the kind of could uh, could prevent this from happening. We have seen examples of this. Um, and I mean, the rest, I mean, I'm not going to spend too much time on it, but this summarizes how we proved it. The thing is that once we have this, I can rescale. If I multiply root n, because this is going at this scale, I can multiply the difference by root n. And so this would be of the order of sigma, and it would be actually random. So it's not going to go to zero. And the kind of central limit theorem kind of characterizes this fluctuation. Okay, so how this behaves after we multiply by this root n. Does it kind of converge in any sense? So that's the idea of the central limit theorem. Questions, comments before we go to? So yeah, the aim is to introduce CLT, and by the end you should know um, what each of them kind of answer. So what is the law of large numbers telling you? What the CLT is telling you? So what LLM leaves out is this. So if you have IID observations, mean, mu, variance, sigma squared, what you have is, by the law of large numbers, xn converging to mu, xn bar, and we know that the standard deviation of the difference is of this order, okay? So you can, this is called parametric rate in a statistic. So a lot of things go down at this rate 1 over root n. So when you say rate, we care about how fast as a function of n it goes down, and the rate is 1 over root n, as opposed to, for example, 1 over n or 1 like e to the negative n. These are different rates. So something that goes down like 1 over n is going down faster than something that goes down like 1 over root n, versus like e to the negative, I don't know, n. This is much faster than this. This is faster than this. This is, for example, faster than something that goes down like 1 over n to the point 1. Okay, so this is the scale that a lot of statistical quantities go, like traditional or parametric statistical quantities goes down. The variance of, so the variance goes down at this rate. The standard deviation goes up at this rate. Um, this is not common, but other certain things might go down exponentially fast. But this parametric rate allows you to kind of scale this. So this is saying the scale at which this vanishes is this 1 over root n. And so what the CLT does is that if we kind of try to, because this is the standard deviation, I can try to divide by the standard deviation because this is the right scale. We kind of normalize it. You've seen this before potentially in other courses. You standardize. You can divide some random variable by a standard deviation. It kind of makes the standard deviation of the result 1. So if this is always true. So if I look at x bar n, I know the standard deviation is sigma divided by root n. So if I divide by this thing will have a standard deviation, which is 1. Um, this you can verify for yourself. I mean, it's a property of the variance. Okay. And if you rearrange, it would look like this. So root n comes out like to the top and you get sigma. So you can verify that this has 0 mean and the variance standard deviation would be 1 for every n. Okay, so this quantity is not going to go to 0. Um, CLT describes what happens to this normalized quantity. Okay, so this is centered around the mean. So the mean is 0 because we subtracted the mean and then we rescaled. So it's going to be variance 1. The question is that does this standardized error kind of stabilize? Is it going to go down, up? Like does it converge in any sense? And CLT kind of answers this. Okay. If you started from the sum, some people would like it like write the sum first. That's going to be the expectation. That's going to be the variance because they're IID. That's going to be a standard deviation. So if you subtract, look at the sum, subtract the mean, divide by the standard deviation. It's different than, for example, here, the mean is mu, standard deviation is this. For the sum, the mean is n mu, the standard deviation is sigma root n. You've seen this before. You do it, you get the same answer. It's gonna like everything that one you should divide by n, both sides, but both the numerator and denominator by root by n, you get the same answer. So it doesn't matter if you start from the sum and standardize, or you start from the average. Okay. Um, Yeah, we talked about why the standard deviation of the sum is sigma root n. So the central limit theorem in the end is either you write it in terms of the average or you write it in terms of the sum. Statisticians often write it in terms of the averages. Is telling you something about the limit of this. What it's saying is that if the xi's are IID, they have variance sigma squared, they have mean mu, um, then so this part kind of these assumptions that we make are almost exactly the same assumptions that we made for the law of large numbers. The assumptions are the same. The conclusion now is, so the law of large number holds, but furthermore, CLT tells you that this quantity converges to a normal distribution normal distribution in distribution. So this convergence here is written with a D on, so this is convergence in distribution. Converge in distribution. So this is different than convergence in probability. Okay, different than convergence in probability where we denote it by P. Okay, so convergence in the law of large number is convergence in probability, and we discuss what it means. This is a new type of convergence. Um, what basically it means in this context is that if you look at the probability that Zn is basically in any interval that converges to the probability that a normal random variable is in that interval. So this is really the probability. Let's say Z is a standard normal. This is different than Zn. Okay, so this is the probability that a random variable Z is in the interval A to B. You can write as phi B minus phi A. Phi here is the CDF. He's written here. Phi is the CDF of Z, where Z is standard normal. Okay. Um, Another way of saying it is like in this case, it would be just a CDF. Basically, this one also converges. you can say the CDF converges to the CDF of the normal. In this case, it's equivalent. So this holds for any t. This is phi of t. This would imply the other one or vice versa. Okay, so this is for a closed interval, this is for half open interval. But basically at the level of distributions, they converge. Okay, so this characterizes the distribution. So this is saying like pointwise, let's call this, for example, phi and t. This is saying the CDF converges pointwise for every t. Okay, and that's kind of one way of characterizing convergent distribution. There are different ways of doing it, but in this case, this might be the simplest. In general, it has to connect, the CDF has to converge to the CDF of the limit at the points in which the CDF of the limit is continuous. And for the normal, every point of the CDF is continuous, so it has to converge to every point. That's right, at every point. Okay, does that make sense to people? So it doesn't say that Zn converges to any fixed point or any particular random variable. It just says that the distribution of it is stabilizing. It behaves like a normal distribution. Okay, this is a little bit shakier than the law of large number because the law of large number tells you that the x bar n is converging to a number. Okay, it approaches that number. This is not saying that this is approaching a random variable, particular random variable, or any constant, but it says that this distribution of it is getting more and more accurate. Like you can tell this distribution perfectly. Okay, any questions? The significance of this result, if you haven't seen it, is that the distribution of these original variables could be anything. They don't have to be even continuous. Um, they don't have to be normal. They don't have to be continuous, nothing, none of that. It just the assumptions are these. And then the CDF converges pointwise. That's the idea. Sorry, give me a sec. Any questions in the meanwhile? So the main point is it's kind of something that emerges from adding many independent contributions and scaling by this proper root and a scale. It doesn't need the individual pieces to be normal. So that's the kind of interesting aspect. So here's an example I think we have maybe last time I showed you. Um, um, so we had the exponential random variable. So this is a random variable that takes non-negative values. So if you look at the density is like um, at zero, it's something and it comes down like at the rate e to the negative, let's say t. Okay, it's 1 here, 0 before, and it comes down exponentially fast. And so you can see it here. This is the density of x1, let's say. This is the density of the average for 5 IID variables with the same distribution, right? So this is that. Um, and then this one is for n equal 25. And so if you look at it, the mean is both the mean and variance are 1. So in this case, basically x bar n minus 1, or rather like x bar n is converging to 1. This is the law of large numbers. And so if I put an interval around 1, the most of the mass is going to concentrate. And if I keep adding, like if I keep plotting, as n goes to infinity, this starts to get sharper and sharper and kind of collapses at 1. Okay, it doesn't show you any particular distribution. It just converges to a point mass. However, if I rescale it, so if I rescale these random variables, um, in this case, I have to subtract 1 and then divide by 1, which is the sigma. The law of large numbers tells you that this converges in distribution to normal. Okay, so I have to plot the density of this, which is not, sorry, it's not equivalent to multiplying. So you're multiplying and subtracting 1 from x bar n and multiplying by root n. It does something to the density, which we haven't talked much about, but um, you can argue for yourself something like this is a transformation. It does like a transformation to the density. Let's skip that part, but you can calculate the density of this from um, the density of x bar n. Or you can plot it by histogram. But anyway, so you can compute the density exactly in this case. And if you plot it, you can see at n equal to 1, basically you see like a very huge, um, I mean, the scale here is like, it's not huge. It's going to be, goes to 1. It's like at 1, it would just be um, shifted version of the original one. But then you can see it starts to stabilize and then the shape gets close to a fixed distribution. It doesn't collapse to anything. So that's the CLT. Okay. So the shape of the distribution of this is going to be stabilizing. Okay. This is not trivial. It's kind of a non-trivial result. And it doesn't matter what shape of the density you start with, it all ends up approximately becoming normal. That sounds good. Any questions? So very different populations would produce the same distribution. That's one of the powers of the CLT. It's kind of a universality result. So it doesn't matter. Sometimes these are called universality. So the underlying distribution doesn't matter. Okay, so you start from, let's say, uh, Bernoulli point 1, for example. If you add a bunch of Bernoullis, it would give you a binomial. Okay, and so if you plot it, I mean, if you properly subtract the mean and normalize, you would get a discrete distribution because the binomial takes discrete values. But these values would the discrete values as n goes to infinity, you get more and more values. So you have values between 0 and n, and if you subtract and normalize, you would get basically any potential continuous values in the limit. And the distribution converges to this continuous distribution. This is an example where we are doing uniform, and this is the histogram, I think, of the limit, and this is the histogram under the exponential. And they all kind of converge to the same thing. Okay. So n here is like n equal 30, I think. This is probably not correct for, um, I don't know where n is here, but yeah, this isn't right. So it seems to be right for the n equal 30. But these other two seems to be at n equal 30. So uniform is close. Exponential is still a little bit skewed, but very close. Uh, with Bernoulli, the discreteness is visible. It could be still like this is 30 because the um, success probability is 1. It's this like the probability mass is a lot of it is located near 0. Um, and so maybe this is correct. Okay, so it's like, and also like it's an asymptotic theorem. It doesn't tell you necessarily how close you are to the limit. Okay, asymptotic approaches, but for 30, the sample size of 30, it's not clear. So here, for example, you get a very good approximation. Here, you're not. Here, you're still like a little bit skewed. So how well you approximate, it's not part of the theorem. Okay, how many samples you need. Okay, is that kind of clear? Um, yeah, I'm gonna skip this. This is not very. So let's do maybe a quick example. Anyone wants to try this? So suppose you have x1 up to x100 and their IID mean is 50, standard deviation is 10. I want to use the CLT. You can use the CLT to approximate um, statements like this. What is the probability x bar 100 is bigger 52? Okay. You could use Chebyshev last time to give an upper bound. Um, that would be a crude upper bound you can compare later. But you can use the CLT to do it would be an exact upper bound. It holds for sure. CLT is not a guarantee in this case because whether 100 is a good end for the CLT to kick in is not clear, but you can get an approximation which would be much better than Chebyshev if you ignore the fact that there's an approximation error, which could be bigger actually than the probability. But how do we use the CLT to approximate this? Anyone? Yeah. So I'm going to write this as minus 50, right? That's so far exact. Then what? You want to like construct this random variable, root n, x bar n minus mu. I subtracted mu, so I have this so far, right? So I can divide by sigma. We can divide both sides by sigma to get the same thing because it's a positive number, right? And then what do we do? Multiply by root 100, right? So a bunch of cancellations happen, so this goes away, right? So this is that my z 100 if you want, that quantity that is approximately normal. Okay, so this is going to be approximately, if 100 is good enough, phi, it's not phi, it's the probability that a normal random variable, let's say z, is bigger than 2. Okay, z is, and this is really 1 minus the phi of 2, but none of which is closed form, but you can compute it, it's going to be small, right? So what is the number? It's just going to be, yeah, 0.02. You can do it via the sum, give you the same answer. Okay, so this gives you like a crude way of approximating uh, probability um, without knowing much about the distribution. Whether this is a good approximation depends. It's not an exact form. Any questions? And this is not very important. This is the same idea. If you do it, apply it to the sum of a bunch of Bernoulli variables, um, you get, I mean, we could do it with the sum in this case. So if you look at the Bernoullis, they're like you have indicators that are Bernoulli, independent Bernoulli p variables. You look at the sum, they're going to be binomial. Um, you take the expectation of one of this is like the sum, right? Take the expectation, you get NP. Take the variance, you get NP times 1 minus P. You subtract the mean, which is NP, divided by this the root of the variance, which is that. So this is saying this is approximately normal. Okay. That's from the CLT. There is a bit of um, in this particular case, there is a bit of a correction that people do called the continuity correction. If you do the, and traditionally, a lot of the CLT idea was trying to approximate these like related to the approximating the probability uh, of this centered binomial random variable. So potentially first proof for this case. But in this case, you can get better approximation than what um, pure what is called pure CLT provides. The reason is if you look at, for example, because it's a discrete distribution. So if you look at the normal density and then you look at um, so let's say if I want to compute the probability that x is less than or equal to 45, for example, right? Um, the the if you look at all the bars when you look at the uh, kind of the probability mass function of x, there is a so this 45 kind of lands in the middle um, of kind of this bar, if you imagine. Uh, so let's see how we can kind of argue. So if you basically, what happens is if you try to approximate it with the area of the normal below 45, kind of you lose half of this kind of bar. The idea is something like that. But if you add that half of the bar, you get a better approximation to. So instead of trying to go all the way to, sorry, to 45, I go all the way to 45.5. So I look at the area here under the normal. This is a better, like this is going to be a much better approximation. It's going to be going a little bit over, but it includes a lot more of the mass that I need that otherwise would miss. So in this case, rather than trying to, uh, so let's say this would be, sorry, if you do it for the sum, roughly what it says is that x is roughly approximately normal with mean NP and variance NP 1 minus p. So this is not asymptotic because asymptotically both of them are going to infinity. This doesn't make sense. But for finite n, this being approximately normal and this being approximately this normal are the same. So if you basically multiply both sides of this by the standard deviation and add the mean, what it does to the normal is shift the normal like this. So rather than if you call this z, rather than doing like if I look at the x less than or equal to k, you're saying this is approximately probability that z is less than or equal to k. The continuity like correction that I was discussing says, and rather than doing that, let's just add 1/2 here. So this is going to be a better approximation. This doesn't follow from the CLT, but in this case, like in finite n, if you do want to calculate something like this, you look at the normal approximation to the sum and you evaluate it on that interval plus like half. If it's like uh, it's going to be always integer because it doesn't make sense to. I mean, the probability that x is less than or equal to 4.5.5 is the same because it only takes the same value, like values 45 and then 46. So any value between 45 and 46 is kind of the same. And that's another way of kind of trying to argue. You can say, okay, this is equal to that, and now this is approximately this. So this side doesn't change, but basically this gives you a better approximation to both of these. Okay, does that make sense? I mean, it's like a pictorial proof, but I think you get the idea. It's just if you think about it and look at the picture, you would realize that basically anywhere from yeah, the question would be whether you can why 0.5, maybe why not like I don't know, do 0.6 or so. But I'm not doing a proof, but just like giving you intuition. It's like a minor point, but it's good to know that for the binomial case there is a correction that gives you a more accurate result. So if you look at the binomial, this is called continuity correction. I don't know if I mentioned it here or not. Right. So if you look at the, for example, binomial with 100 and point 4, the normal would have mean, which is NP. NP would be uh, what would it be? 40. Yes. And then the variance would be NP1 minus P would be 40 times zero point 0.6, which is 24. Okay, so mean is this, standard deviation would be root of that. So you would look at if we want to compute this is going to be the approximately probability that a normal variable z is less than or equal to 45 minus, sorry, z would be, I shouldn't call it z, but let's say a normal random variable would mean 40 and variance 24 is less than, so we're computing this. And this is really phi of, you can argue for yourself, it's like the probability that n is less than or equal to 45.5. So again, you write it as the probability that subtract the mean um, minus 40, and then you divide by the standard deviation. These are all the same events. And then we recognize that this quantity here, this is now standard normal distributed because the original one was this normal. And so you'd get the probability that standard normal basically is less than or equal to 45.5 minus 40 divided by root 24, uh, which is just going to be the phi of that number. Okay, I assume this calculation is standard for you guys. So if you want to compute the probability of normal distribution is less than this, you subtract the mean, divide by the square root, and you transform it into a probability statement about standard normal, like this, and then you can write it in terms of the CDF, and then you can evaluate it, and it turns out to be that, for example. Okay, and the exact value happens to be, in this case, that, and you can see is very close. If it did not do the continuity correction, or half unit correction if you want, um, what you would get is you can go and calculate it. You get this, which is a little bit off. Still close, but um, that correction makes it a little bit more accurate, rather a lot more accurate. Okay, so I just leave it as a like something good to know for the binomial case. If you want to use the CLT, there is a better, slightly like a trick. Just if you want to evaluate it as uh, an integer, you compare it with the normal, the correct normal with the mean and the variance matching, but at half an interval above that, that would give you a better approximation. Okay. Yeah, this one is another example, which I'm going to probably skip. The same kind of goes here. So if you want to do a binomial, 55 to 70, um, then you can go 5 point below and 5 point above, and that will give you a better estimate. Uh, it's the same idea. Or you can think of it as just basically subtracting two different probabilities. It's like this minus the probability of x less than or equal to 55, and you just apply continuity correction to both. But I mean, this one is on the other side. It's a little bit tricky. Well, I'll let you figure it out. Just argue for yourself that this is the right way of doing it. Um, Writing it this way would be a little bit more tricky if you wanna. I mean, it's just yeah. In this case, this would be a little bit different because you shouldn't write it that way because the really this would be like x less than or equal to 17 minus, if you want to be precise. This is an example where precision matters because you have equal here. This would have to be like less than 55, which is different than equal because in this case, x really jumps at 55. So don't do it that way. That was not a good idea. Just do it like this and then argue by something like the picture. That it's good to like go, for example, if you want to compute 35 to 45, it's good to go zero point 0.5 below and capture the entire mass here as well as the entire mass. So that's the idea here. So you go uh, calculate the probability that normal with the corresponding mean and variance is within this range, and that gives you a better approximation. Yeah, this is another application of that idea, which we did not. So by the way, I haven't proved CLT. If you get a chance by the end, if I have time, sorry, give me a sec. Okay. All right. Okay. Questions? So this is another, I think, application. It's just the same thing, but like in different disguise. So if you have like a respondent, uh, I supports proposal, uh, um, like a given proposal. So let's say, okay, yi is the indicator that respondent I supports a proposal, and if they don't support it, it would be zero. Okay, and if you have like a poll, yes or no poll, then you want to see what percentage supported. It would be just the n average. Okay, and in this case, you can again model them as by Bernoulli's, and the average would give you the in language of statistics unbiased estimator of p. So the expectation would be p, which is what you want, and the standard deviation would be this. So you'd have some sort of an approximation. So this is really example of the same thing that we did here. It's nothing new. This is in terms of the sum. That's in terms of the average, which is like a you can think of it as a estimate of a probability or frequency or rate. Um, right. So for example, if you have um, this is an example where it gives you like a good measure of like fluctuations of the uh, pole. So you want to like you care about, let's say, this value, but what you observe is this value. So the question is that how accurate uh, p hat is as a an estimate of p, and the CLT allows you, because p hat minus p divided by this is approximately normal, you can kind of build a confidence interval. That's the statistical uh, like basically use of the CLT. So what you can say is like how reliable basically this p hat is as an estimate of p, right? So anytime you have a like an estimate of a frequency, you can ask this: what is uh, let's say you're basically taking a poll. Let's say 30 people attend versus 300 versus 3,000. How can I get an estimate of like how accurate in each case the poll is? Okay, so what you can do is um, if you rewrite, yeah, so this is saying p hat minus p divided by the standard deviation of it, which is really that root p times 1 minus p divided by n. Again, this is an average, right? So p hat is an average of the responses, the indicators. And so we know that the mean is just the mean of one of them, which is p. So yi's are Bernoulli p. And the variance would be just 1 over n variance of one of them, right? Yi. So we p times 1 minus p divided by n. That's the variance of Bernoulli divided by n. So standard deviation would be root p1 minus p over n. So the CLT is saying, you can again argue it differently, but if I look at p hat and standardize it, this is an average. Subtract the mean divided by the standard deviation, p1 minus p divided by n. This converges to a normal distribution. And that's the CLT in terms of an average. And so what I'm doing is basically saying that the probability that this quantity, p hat minus p divided by a square root p1 minus p divided by n is bigger than or equal to, or let's say, okay, less than or equal to t is converging to the probability that the normal, standard normal, let's say z is standard normal, is within that interval, okay? And let's say if I want to make sure, for example, that my estimate is uh, basically what I want to do is that I want to give you an interval that I'm sure that contains the true p with high probability. This is called the confidence interval in statistics. So what I can do is that I can pick t such that this side is 0.95, let's say. Okay, 95% of the time is true. So that t would be 1.96, for example, because this is normal. We can go check. If you have a normal random variable, you go look at the tails, how far in the tails you have to go such that the mass below minus t and above t together sum to 0.05. Okay, because symmetric it would be 0.025 here and 0.025 here. So the mass outside that interval is 0.5. The mass inside would be what is left over here is going to be 95%. So that t is approximately 1.96. So this is saying if I put 1.96 here approximately for large n, the probability would be close to 95. Okay, and then if I rearrange this is an event. If I multiply both sides by the variance, I get p hat minus p less than or equal to 1.96 root p1 minus p divided by n. Okay, so this result that I've shown here. So the probability that this event holds is approximately 0.95. This comes from the CLT because I picked 1.96 based on the tails of the distribution. This is not normal, right? But the CLT allows me to translate this probability in terms of the complicated distribution of p hat to the simple distribution, which is Gaussian. Okay, um, and so that's the CLT. Now this allows me to state something like this because this you can interpret as p belonging to an interval centered at p hat with this length. Okay, so if you look at this, this is equivalent to saying p belongs to an interval that has these two endpoints, p hat plus minus. So you look at p hat, and then it's p hat. Let's say this is, I don't know, gamma, p hat plus gamma, and then p hat minus gamma. So that event is saying p belongs to this event is equivalent to p belongs to p hat minus gamma and p hat plus gamma, where this is gamma. Okay, this is another way of writing it. And so this interval is called a confidence interval. Okay, it's a random interval. Um, but what we're saying is that the true p, which I don't know belongs to this random interval, would probably be about 95. So if you repeat the experiment many times, 95% of the time, this interval that we constructed would contain the truth. Okay, and then this is for, okay, this is not, yeah, so this is gamma. Here we have gamma hat because let's say this is also dependent on p. I'm being a little bit, this is another level of approximation. So what we have is like two levels. So first we say the probability that p belongs to p hat minus gamma p and p hat plus gamma p is 95%, but the problem is that this also depends on p. I'm gonna say, okay, I'm gonna approximate p with p hat. So I get p hat minus, it seems circular, but what um, because we are already approximating one level, why not two levels? So this also be approximately 0.95. Can make it a little more precise, but once you do this, now this quantity is not dependent on p anymore. So this is a valid confidence interval. Here it's not a confidence interval because this side depends on p, but I'm gonna say okay, p is approximately p hat. I'm actually making an error here, but the same exact error that I'm trying to quantify is there. But asymptotically, what happens is that asymptotically, as n goes to infinity, because by the law of large numbers, we know that p hat converges to p. So asymptotically, this approaches uh, this value. So that's going to be fine for large enough p, because it's a continuous function um, of p. Like gamma p is a continuous function. As p hat approaches p in probability, uh, gamma p hat is also going to approach. This is a result in that conversion probability called continuous mapping theorem. Gamma hat at p also approaches gamma p, so it's not a bad approximation when n is large. So anyway, so once I plug that in, I get that p belongs to this interval with probability about 0.95, and this is a valid confidence. Like it's not valid, it's like a asymptotic confidence interval. Okay, this gives you a random interval that contains a truth with probability at least 95%. This gives you a way to measure the uncertainty. You can see as n goes to infinity, this interval shrinks at the rate 1 over root n. So the length becomes smaller and smaller. So your confidence interval like is approaching the p hat, and you can easily kind of uh, basically measure both the center, which is your estimate, and also how much uncertainty you have by reporting this confidence interval. Okay. Any questions? So that's the main application of CLT for statisticians, or at least traditional statisticians. More advanced, there are more advanced applications, but traditionally people have used CLT to get kind of universal confidence intervals in the sense that asymptotically you don't need to, in this case, we know what the distribution of p hat is. Kind of p hat would be, actually at least n times p hat would be binomial. But building a confidence interval based on binomial distribution would be difficult because you have to calculate this probability exactly. CLT tells you like you can do it approximately, and it also approximately holds for many other averages. And so if you replace this with x bar n, for example, this with mu, and this with the variance of the random variable, this will hold basically for any average. The same calculation that we did exactly goes through because this follows from the normal part. And the variance of x1 divided by n is just the variance of the average. So this calculation exactly applies to the general average case, or sorry, the mean. So you can compute the, I don't know if I have it here or not, but same calculation. So x bar n plus minus 1.96 root, let's say variance of one of them divided by n is approximately 95% confidence interval for mu, the mean of the distribution. This is the general kind of form of the using the CLT as that. So in this case, the variance happens to be dependent on the mean itself, so we needed to replace it. But sometimes you know the variance, so you just can plug it in. So that would be good enough. Yeah, so I mentioned this. So this is still has the unknown p, you replace it, and then this gives you the confidence interval. So right, so you could do examples. For example, if you have a poll of 1,000 respondents, basic any question before we go, this is kind of important. Any question about this example, how we come up with the confidence interval? Questions, comments? Okay, so example, you have a poll of 1,000 respondents, each one giving, let's say, binary response, and you average, basically, you get p hat is 0.54, right? You want to find an approximate 95% confidence interval. Okay, confidence. Anyone? What will be the confidence interval here? I think it's not very like informative. You just plug in, right? So you get p hat, which is 0.445 plus minus 1.96 root 0.5, 1 minus 4.5, 5.4, and then divide by 1,000. Okay, and then you just do the calculation, ends up being um, uh, I mean, that would be this much, and so you get this minus this plus that. And so with 95% confidence, the true value would be between these two values. So if you repeated that, like this is the meaning, right? So if you do the frequentist meaning is the probability of this is approximately 95. So the meaning of the confidence interval doesn't mean that the truth is in this interval. It means that if you repeat the experiment with another 1,000 respondents, you get a different value here. And then you do this calculation, you get a different interval. It might be something like that. Next time it will be this. Next time it will be that. Next time it will be this, and so on. 95% of them, whatever the truth is, 95% of these intervals would contain it. Not that this particular realization contains it. Okay, it's like a typical frequentist interpretation, which is often misjudged. Although in practice you just observe one of their realizations, and that's you have to be happy with it. But the truth could be outside. This could be one of the 5% of the time that doesn't cover the truth. Okay, it's really a frequentist idea. If you really want to capture the 95%, you have to repeat the experiment. You get many different intervals, many different values here, many different here, and then the interval would change. But as it fluctuates around, it captures the truth 95% of the time. Um, okay. Another way of doing it, you could do um, an upper one. I'm going to skip this maybe. Okay, so what I want to do is try to actually prove this. You can read this part. So we started with discussing this, but the and you see some applications of it. There are more applications. But why this result is true. Um, so we didn't really prove it. Okay, we proved this, the law of large numbers, but we didn't really prove the CLT. So I just want to prove it. And there are different ways of proving it. And there are many different ways. The way that I want to prove it is perhaps simple and a very common way. And the idea is to use the moment generating functions. Okay. And before introducing that, how many people have gone to the discussion? Oh, I see that Hayden has produced a solution to this. Yes, so the solution of Hayden is exactly as I didn't make it enough. I didn't wait enough for you guys to answer, but yes, that was the correct answer. So how many people have gone to the discussion where Ethan talked about MGFs? Let's see how many people know about MGFs. Did you get a chance to go to the discussion? Momentary functions? Anyone? What is a momentary function? I want to prove the CLT. Generating function MGF. Find mean variance for distribution. That's a very that's yeah. So MGS allows you to find the mean and the variance for distribution, but that's like selling them short, right? It's like saying that you get a PhD to be able to calculate 2 plus 2 is equal to 4. It's true. I mean, it's not 2 plus 2 maybe. You get a PhD in statistics to be able to, uh, I don't know, compute an average of a bunch of numbers. That's true. You can do this if you do the PhD, but there's a lot more. It can tell you the mean, variance, skewness, kurtosis. Okay, so that's JT. So this is a little better. So it tells you more. So mean, variance, skewness, kurtosis, right? Uh, so the main idea is that it gives you another representation of the distribution, which is kind of equivalent. Okay, so mean and variance are um, kind of summary statistics of a distribution, but they don't um, pin the distribution down. So there are many distributions that have the same mean and variance. And in fact, the CLT tells you that basically once you have a sequence of IID random variables that have the same mean and variance uh, as a normal distribution, their average kind of converges to the normal. Okay, so any distribution, I mean, you can have many, many different distributions with the same mean and variance. And in particular, you'd have a normal distribution with a given mean and variance. You can add skewness and kurtosis. These are higher order moments. And so um, there are more like descriptions of other features of a distribution that may not be um, implicit in the mean and variance. And for a normal random variable, for example, if you specify mean and variance, you specify the full shape of the distribution, it implies all the other moments as well. But it's more than that. It's even more than a skewness and kurtosis. I want to see what else people can come up with. So I mean, this is an important, like, conceptual idea. Did um, did Ethan talk about uh, like deeper kind of intuition or idea behind the MGF? Why are we looking at homogeneous functions? So if you recall, let me go back. If you recall, the distribution of random variable is a map that maps um, every subset of the reals to the probability. So it's a function that tells me what the probability of an event, or not event, but like x belonging to a subset of reals is. Um, Having the mean and variance is not going to be enough to answer this, for example. Another way of doing this is, rather than writing this, I can write this as the expectation of um, an indicator. Okay, so the indicator that x belongs to A. Okay, or you can write it like this. If you have an indicator function, if you apply it to x, so indicator A of little x is saying x belongs to A, and sorry, 1 is if x belongs to A, 0 otherwise. Okay, so if you look at the indicator, it's a binary variable. If I take the expectation of that binary variable, that particular indicator, it tells me this probability. Okay, now um, if I vary this for all possible indicators, I get the distribution. Okay, so you can think of the distribution as the set of all these numbers when I look at this is a function. So if I look at the general function of x, okay, if I look at these numbers, as g varies over all the indicator functions, indicator, the binary functions, okay, functions of x, we get the whole distribution. So the distribution is all these expectations for g ranging over all indicator functions. If I now restrict myself, so if we restrict g not to indicators, but to polynomials. Polynomials, polynomials. We get moments, okay? You can think of these g's as probing the distribution. So if I give you a g and you compute the expectation of g of x, this is one summary of the distribution. You're probing the distribution by applying the function to the random variable and reporting the mean. That's one particular summary. Okay, so g of x, for example, being little x gives you expectation of x. That's one summary. If I take g of x to be x squared, I get e of x squared. That's the second moment. And if you have these two, you would get the mean and the variance. I can take g of x to be x3, and then you get this, and this has more information potentially than other two, and then you can keep going. Okay, you can keep um, looking at all polynomials of all degrees, or I mean, polynomials would reduce to these monomials. So you can look at g of x, xn for any n. And so these produce moments. And these are probes of the distribution. If you give me all the moments, I might be able to pin down the distribution. That's the idea behind this approaches, is that how many of these functions, how many of these probes we need to be able to pin down the distribution. In the case of the original distribution, all the binary functions would suffice. For certain distributions, all the moments would, so moments would be polynomials, polynomial functions, or monomials really. If I give you all the monomials, sometimes it might be enough to determine distribution. Um, so there's certain distributions for which this is not enough. The MGF is another class of functions. It tells you, okay, I'm going to look at all these probes, but I'm going to take G to be the set of all exponential functions. So e to the tx for all t. Okay. And that's kind of going to be enough. So this is the idea of the MGF. Look at the exponential probes of the distribution by applying like e to the something, like I can have, for example, e to the 1 times x, take the expectation, e to the, I don't know, 2.5x, and so on. And in general, I would look at e to the tx as t varies. So if I look at this map that maps t to that, for all t, when I look at it, I get a function. It would be like a continuous function. This is, I might write it as mx of t. That gives me the moment generating function. So it turns out that this information is enough to reconstruct the distribution. If I have this information, I can reconstruct, for example, the expectation of all the indicators, and then so I can like reconstruct the distribution. As a byproduct, this allows me to reconstruct the moments because if I know the distribution, I can reconstruct the moments because once you have the distribution, we really didn't talk directly how to, but having it for binaries, you can probably already know how to compute the mean from the distribution. But this kind of gives you can prove that this is enough to be able to calculate the expectational indicators, or really the probabilities of x being in any event. And from this, you can get all the moments. The interesting thing is that you also get directly the moments by differentiating this. That's kind of the idea behind why it's called moment generating function. But the main point is this is probing the distribution via the exponential distribution gives you like a different view. It's like a transformation of the distribution into a different um, um, like in a different domain. Rather than looking at distribution uh, as a map from events or like sets to probabilities, you look at it as uh, a function, a univariate function, which is the expectation of these exponentials, and that's enough to reconstruct the distribution. This is like if you have seen it in probability, sorry, in typical math courses. You have a function and you transform to the Fourier domain. You get a different representation of the function. This is exactly similar to that. This actually corresponds to the Laplace transform. If you look at e to the I tx, or omega, let's say. I is the complex number. This gives you a different view. This is called characteristic function, and these are also going to be enough to reconstruct the distribution. Um, okay, does this kind of make sense? I haven't proven it, but the main point is the idea behind it is that I'm going to look at expectation of g of x. G varies over a class of functions. So what classes of functions can I look at that allows me to characterize the distribution? Once I have that this values, these probes for all g, then I can uniquely characterize the distribution. The class of these functions is enough, and this leads to an MGF. The class of all indicators directly gives you the distribution. There are other ways, like the class of complex exponentials, also enough. That would give you characteristic functions. The class of all polynomials sometimes is enough, not always. But I'll leave it at that. Okay, that's the general idea behind MGF. So potentially it gives you, once you have it, if you believe it, it's enough, then it gives you the mean, variance, skewness, kurtosis, the probability of anything that you want, all the moments, all the higher order moments, anything that you can get from a distribution, you get from that. Questions? So let's maybe see how you can directly get the moment. So if you look at it, it's just another, if you ignore the intuition behind what I mentioned, like the general big picture, if you look at this, you can expand the exponential. You can already see the moments. This is like Taylor expansion. Right, and then the expectation passes through. It's like an infinite sum, but it passes through. We haven't talked about this really, but you would get something like this, plus t squared over 2. That the first one is Taylor expansion. The second is expectation passing through the sum. So MGF has this expansion, and you can see the moments sit at the coefficients of different terms, right? So if you if you compute this and then do a Taylor expansion of this, then the coefficients would tell you the moments. Another way of seeing it is that these, when you do the Taylor expansion, you take the derivatives. The coefficients are related to derivatives. So if I take the first derivative of mt, it would be like this would be 0. The first one would be expectation of x plus this would be t times expectation of x squared, and so on. So if I evaluate it at t equals 0, you can see that this goes away in all the higher order terms, and so I get uh, the first derivative relative to 0 gives me the expectation. Okay, and then if I differentiate twice, uh, this one go away, I get expectation of x squared plus this would be t to the third 3 factorial, expectation of x3. Right, you do it first, would be t, this would be t squared over 2 factorial expectation of x squared, x to the third. Um, the uh, yeah, so this would be potentially t if I'm not wrong. Plus the rest. So when you do evaluate that at t equals 0, you can see that higher order terms go to 0 and you get the second moment. Okay, and so on. The Does that make sense? So you can already see that it contains all the moments directly. Um, but it also has all the information about the actual distribution. You can compute the probabilities. Not directly, but if you have it, you should in principle be able to calculate the probability of events. There's another thing which is like log MGF. This is called cumulate joining function, and this has the same information as the MGF. If you differentiate this, you get the cumulants directly. So the first cumulant is the mean, the second cumulant is the variance, and so you get it directly here. You get the second moment you have to calculate the variance by hand. Um, Anyways, so far, I think potentially at least some of this should be clear to people. So let's see. Um, uh, I want to know proof, given we have about 20 minutes. Let's see if you have it on this slide. Um, uh, did what is it? Did Ethan talk about the MGF of the normal? Did he talk about the MGF of standard normal? Anyone remember? So if you really want to calculate the MGF of a random variable, so let's say z is normal, which means 0 and variance 1. Okay, yeah, so if you have it, then how do I calculate the MGF? I want to compute mz of t, which is expectation of e to the tz, right? Um, yeah, we don't have much time to, I want to try it. Uh, you already know how to do it. It's just this law of unconscious statisticians. You can, for any distribution, you can do. Sorry. Okay. Paste. So I have, let's say, standard normal distribution, right? And the MGF is just this expectation is just a function of the random variable. I can use the law of unconscious statistician. So it would be integral e to the t z level z, and then times the density of z dz. Okay, so it would be integral e to the t whole z, and then 1 over root 2p, or 2 pi e to the negative z squared over 2. Anyone remembers how to calculate this integral? There's a trick here. This is a minus infinity to infinity. Anyone? The trick is like completion of a square. So you have tz minus z squared over 2. You complete this square. Anyone knows what that means? I'm going to do 1/2 z squared minus, or is this minus or plus? Uh, Plus, right? If you rearrange factor, yes. So what we want to do is we want to like do like something like this. So if you do this, so far I think it's so good. I mean, this if you rearrange, you would get tz comes out here. Oh, actually, there's a negative sign here. Yeah, it should be negative. So negative 1/2 times negative 2 goes away. You get 2tz and then the first one. So this is so far so good. And then what you want is like, you want this to be a complete square. So z minus t squared. This gives you the first two terms, z squared minus 2tz, and then plus t squared. But I don't have the t squared, so I'm going to subtract the t squared. Okay, so that's completing the square. It's the same thing, right? If I now plug that in, I get 1 over root 2 pi integral e to the negative 1 half. You get z minus t squared minus t squared. Okay, notice that this just factorizes because exponential is like this. You get e to the negative 1 half z minus t squared times e to the negative the other one, which is like just going to be 1 half t squared. Okay, and then 1 half t squared is not dependent on z, so it comes out. So I get e to the 1 half t squared, and then I'm going to move the root 2 pi inside. I get root 2 pi e to the negative 1 half z minus t squared dz minus infinity to infinity. This is really the standard normal distribution, like the density, the integral shifted. This is really the density, integrating the density of a normal distribution between t. So this has to be 1. You can do it by change of variable or just noticing that this is this part is really density of normal between t and variance 1. And so it has to integrate to 1. So the end result is that it's just e to the 1 half t squared. Okay, so that's the NGF of the normal. If you take the derivative once, so m prime x t would be e to the, um, sorry, it would be t e to the 1 half t squared, right? So evaluate that t equals 0. Gives you 0, so it's like a first check. And if you um, do the second derivative, you get 1. Another way is just to expand this. If I expand it, I know that e to the x is like 1 plus x squared over 2, blah, blah, blah. If I expand it, you get e to the 1 half t squared is 1 plus 1 half t squared plus um, um, what would it be? Yeah, 1 over 2 times 1 half t to the 4, and so on. And you can see you have to compare it with the Taylor expansion. If you do Taylor expansion, this is m x of t or a z of t. So if I do the Taylor expansion, I get 1 plus the first derivative um, times t plus 2 t squared plus so on. Basically, if you compare, you have to account for these facts. But if I, or you can see that the expectation of x, let's forget about this part. Um, Once I did the expansion, you can see like um, the coefficient of t is expectation. The coefficient of t squared after I put a 1 half here would be so t squared over 2, the coefficients would be the second moment. So if I look at the t squared 1 half, you can see there it's just multiplied by 1. It's just multiplied by 1. So 1 is the second moment. So the second moment is 1. The third moment is not there because um, there's no third term. So the third moment is 0. Gaussian is also symmetric. That's also clear. The fourth moment you can read is like it's going to be 1/8 t to the 4. You have to compare with the fourth. The fourth term here is going to be t to the 4 divided by 4 factorial e to the expectation of 4. So you have to compare this 4 factorial. You factor 4 factorial out, compare it with 8. You get what the. I'll let you figure out. You can compare it basically with this series expansion of the generic one with this, and you can read all the moments. Anyways, um, we don't have much time. So that's the NGF of standard normal. Okay, so um, so now if you want to like understand what the CLT does, so if you look at the NGF of the standard normal, if you expand it, the first two term would be as we did above. It's like 1 plus 1 half t squared plus something which is in this case, it's actually going to be O of t3, but let's say in general it would be O of t squared. Uh, it goes down faster than t squared. Okay, low O means it goes down faster than t squared. But the first two term looks like this. So now if you look at the general random variable, if you look at the centered version, minus mu and divide by the variance, then this random variable, this is not normal. This is zero mean, and it's going to have a variance of 1. That's by the standardization. Now, if I look at the MGF of this, the standard variable, random variable, you get this is going to be 1 plus t times the expectation plus t squared times the expectation of t squared plus higher order terms, terms that go to 0. So this is 0, and this is 1, right? So if you look at the first two terms, exactly match um, the MGF of the Gaussian, right? So the idea is that if you have a centered random variable, the MGF of the second order uh, would be the same as the MGF of the Gaussian. The question is that what happens to these terms? For a single one, these terms would be different than the Gaussian. So the Gaussian would have a different term here. A general random variable would have a different thing. But as it happens, if you take the average, this part ends up kind of approaching uh, the I mean, let's do it. But the main point is the equality of these two parts. So let's do the actual proof. Um, let's look at the sum, and I'm going to assume that I mean we already standardized. So these random variables have zero mean and variance 1. So if I look at the sum version of the CLT, I have to sum divided by the standard deviation of the sum. The standard deviation of the sum would be root n times the standard deviation of one of them, which is 1. Okay, so if I look at the sum wi, the variance would be summation of the variance of each one of them. So it would be n times the variance of one of them, which is 1, right? So you get n. So the standard deviation is, I mean, these should be already very standard. So the standard deviation is root n. So this is zero mean, so I don't have to subtract anything already subtracted. But the variance is n, or the standard deviation is root n. So if I divide by root n, this is the form that is gonna, we have a CLT form. So this we want to show that converges to um, normal in distribution in the limit. So if I look at the expectation, I want to look at the MGF. So MGF of Zn would be expectation e to the t Zn, which would be expectation e to the t. I get basically W1 up to Wn divided by root n. Okay, and so this factorizes. So you get expectation of e to the t W1 root n times e to the t W2 root n dot e to the t Wn root n. That's the property of the exponential. Okay, exponential, the sum is the product of the exponential. So far, we haven't used any probability. Okay, I don't think I can. So the independence comes in here. So if you remember, the expectation of the product of independent random variables factorizes, so we use the independence. So this gives me expectation of e to the t W1 divided by root n, e to the W1 divided by root n, dot e to the t Wn divided by root n. So that's independence. And then we use this fact. So for each one of them, I have this expansion. So expectation of e to the wi is 1 plus 0 times t squared over 2. This is going to be 1 plus O of t squared. So if I look at e to the e to the t over w I divided by root n. You can see the root n here. You get 1 over 1 plus, this is equivalent to applying the first one with this t. Okay, I'm just, this is a function of t. I can apply it with any t. I'm going to apply it with t over root n. So I get 1/2 t over root n to the 2 plus little o of t over root n to the 2. Right. So I get 1 plus 1/2 t squared over n uh, plus O of t squared over n. Okay, so that's what we have. I'm going to plug that in. Okay, so you get basically a product of these. I'm going to write it as product expectation of e to the t w I over root n. Each one is 1 plus, from above is like 1/2 t squared over n plus O of t squared over n. Um, and really t squared doesn't matter. T squared is fixed. I'm going to just write it as O of little 1 over n because um, we care about how it decays as a function of n, not t. Okay, so all of them have this form, and I have product of n of them. So really what I'm going to get is 1 plus 1/2 t over t squared over n plus all of 1 over n to the power n. Okay, the end result would be exactly this. So if you evaluate this, you get this to the power n. That's what we got. Okay, and at this point, you would use the common fact, like a well-known fact. So if this wasn't here, you probably know this converges to, it's like if you have 1 plus a over n to the power n, what does it converge to as n goes to infinity? Anyone knows? This would converge to e to the e, sorry, e to the a. So this would, I mean, this part doesn't matter because it's going down to 0 faster than this term. Okay, this little o means faster, so it can be ignored. It's as if it only was this here. So it goes to e to the a here would be 1/2 t squared. You can see it's an application of this with a being 1/2. Okay, so what we proved is that the MGF of this would converge to the e to the 1/2 t squared. And that's kind of the um, CLT, right? Um, Basically, you can see that the effect of the higher order term kind of goes away. Uh, and this part is from the first two, which match um, the corresponding ones for the Gaussian MGF. So I proved that this converges pointwise to that. I didn't prove that this means convergent distribution, but it does. I mean, this you have to accept. Then later proved in a different course. Once you prove that an MGF of a random sequence of random variables converges to an MGF of something else, then it means that they converge in distribution because they have equivalent information. Okay, so you can see the MGF approaches proves the CLT. The main reason why MGF is useful is this fact. It's not necessarily that you compute the moment, it's the fact that the MGF of a product basically turns the summation of independent variables into products. So if you have X and Y that are independent, if I want to compute the MGF uh, of the sum, this is the expectation, it would be factorized into expectation of Tx times the expectation of Ty. So it's the product of the MGFs. So it allows me to calculate the MGF of the sum or rescaled sum or averages if you want as if they're independent as the product of the MGFs of the individual ones. This is not the case for the distribution. The distribution would end up being like if you look at the densities, for example, there would be convolutions. It's a harder, much more um, challenging operation in terms of the distribution. They're not products of distribution; they're convolutions. But the MGFs are products, and so this makes it simple. So that's the main reason why people look at the MGFs. They turn MGF of the sums into products of the MGFs for independent random variables. Okay, so that's basically the proof of the CLT, and kind of we're out of time, but that's all I wanted to talk about. It's worth going through this. It's a really simple proof. The only thing that we didn't prove is that convergence of MGFs is equivalent to convergence of distribution, but if you believe that, you can see the main use of the MGF is turning independence, like dealing with independence, like turning independence into a useful fact about the MGFs of sums of random variables. So it's very useful when you have sums of independent random variables. If you want to study them, you look at the MGFs of it. You take the limits and stuff. It would reveal things very easily. Okay. Yeah, I'm gonna stop here. Next time, I'm gonna have just maybe about 1 hour of kind of wrapping up. Just we go over all the things. It's like a review basically, nothing new. And then we'll